element and something called the symmetry operation. We'll leave symmetry operations to the end. And then what we'll end up doing is we're going to put all of these symmetry operations together into something called a point group. Because remember I told you, what we're trying to do is we're trying to classify objects or molecules most importantly, by their symmetry elements. And so what we're going to end up doing is we're going to get one designator that encompasses all of the symmetry properties of a molecule or an object, the symmetry properties being both elements and operations, and have one unifying designator that can describe all of those things. That is something that's going to be called a point group. Well, what we're going to do first is determine what all those things are, these elements and operations. Okay? So, here we go, intro to symmetry. We just finished this off. These are the learning goals from last time, so I'm not going to go through them. The last one that I'm just going to go through is we're also today going to learn the difference between a symmetry element and an operation. Okay? So, here's where we left off. We started to discuss and consider a axis of rotation. Okay? We've designated that as Cn, where n being the number, the number that you can divide 360 by that returns the object to the exact same orientation. I think we did this pretty well, so I think we'll go pretty fast. And office hours were any indication, looks like this is pretty straightforward. So real quick, how many different Cn axes are in this snowflake? How many different ones? So what is there very obviously? C6, right? And we're going to call that C6 the what? The primary axis of rotation, because that's going to be the highest order n. Okay? So we're going to say that this object, the most dominant symmetry operation or symmetry axis is going to be that C6, right? It goes right from the point, the central point of that snowflake, in and out of the board, right? Rotate by 60 degrees, the object is unchanged, a C6. Okay, but what else is there? C3, 2. Okay. All right, so I heard what? What's the next, how about we do it this way? What's the next highest order axis of rotation? C3. And we can see that here, right? Same place where the C6 is, you can see that if you take this center, this top spot here, and then you have a 120 degree rotation here or here, that's a C3, sort of like the Mercedes-Benz propeller, okay? What's important here is that that C6 also contains that C3. So that C6 and that C3, we're going to say are coincident or they're parallel. Okay? The exact same axis can be the C6 or it can be the C3. Okay? So is there another axis of rotation that is coincident with those two? C2, right? So if we go from the top spoke here, we rotate 180 degrees, 360 divided by 180 is 2, or 360 divided by 2 is 180, right? That's going to be a C2, and we can take any point and rotate 180, and the object is going to be unchanged. Awesome. Does everybody see that? 3 coincident axes of rotation, right? And it's not a coincidence that the other 2 axes of rotations are factors of the primary axis of rotation. Remember what I just said, factors of the primary axis of rotation. So for example, if you had a C4, what else are you likely going to have? C2. If you have a C5, what else are you likely going to have? That's a good one. C1, which is not. Yeah, because there's no natural factors to find. That's right. Excellent. Okay. Okay. So, are those the only ones? Is there a C4? Okay. Now, here's the question: are those the only CNs in this molecule? And obviously, ones that are those are ones that are coincident with each other, but are there others in different places? Somebody. Yeah. What's your name?
Brian.
Brian.
Yes.
Anywhere?
Like anywhere that it bisects.
Okay, yeah, so there's a perpendicular C2, right? We all know where the primary axis of rotation is, the C6. Is there a C2 right here, perpendicular in the plane of the board? Right here, that bisects, let's say, this edge and this edge. Is there a C2 there? So if I take, right, an axis here, and I rotate 180 degrees, is the object unchanged? Yeah. Right? And you could probably see there's a C2 through any of these opposing edges. Okay. Everybody see that? Perpendicular C2. Is there another perpendicular C2? That's 3 more, right? Depending on, right, which edge you're looking at. Any more C2s? Yeah. What's your name? Patrick.
And it's very important to the warning.
The vertex. Right? That's right, right? So if you take any of these spokes, right, you can pass the C2 axis through one, let's say this top spoke and this bottom spoke, there's another C2 axis right there. So if you have an axis that goes right from the top of the board to the bottom of the board and you rotate 180 degrees, does that leave the object unchanged? Yeah. This one goes to here, this one goes to here, so on and so forth. So there's essentially 3 more perpendicular C2s. So for a total of 6 perpendicular C2s. Okay? So that's the thing. These objects, right, can have multiple axes of rotation. That's just a snowflake. It's actually got a lot. Okay? Let's try this. What's this? An octahedron. Okay? Octahedral symmetry. What does that mean? It obviously looks like an octahedral metal complex, but what's really important, now this is the difference between symmetry, as we're going to discuss, and then coordination geometry. You can have an octahedral metal complex that's a 6-coordinate complex where all of the ligands are arranged, right, in the corners of a regular octahedron. That doesn't mean that that octahedral coordination complex has octahedral symmetry. Octahedral symmetry only happens when each of these points or objects or ligands or whatever they are on the corners of the octahedron are what? The same. Okay? Coordination geometry and symmetry. Lots of times they are the same. More often than not, they are different. Okay? So keep that together in your minds. So now, how many different CN axes are in this octahedron, and what are they? So what's the primary?